mass of the copper coin, A is the mass number. So in this way we can find out N, that is total number of copper atoms. So N is equal to, Na we know 6.23, Avogadro number, everyone knows this well, right? Into 3 gram divided by mass 63, mass number. So we'll get some 2.86 into 10 raised to 22 atoms. Okay, now what we need, we know binding energy formula, delta M C square. In this case you can take it as delta M 931 mega electron volt, as we have calculated before. So you should do this part. You will get some value, that is 536.42 mega electron volt. Now after this we have to find, now we know after getting this what we can what conclusion we can get is how much protons and neutrons are present. After getting N, we can say 29 protons and 34 neutrons are present, right, in copper coin. After calculating N, we can come to the conclusion that 29 protons and 34 neutrons are present in the nucleus of the copper. Now we have to find nuclear force, right? So how we can find out? So nuclear force is or the binding energy to separate protons and neutrons present in 3 gram of copper coin, right, is equal to N into binding energy, number of atoms into binding energy. So number of atoms we got 2.86 into 10 raised to 22, whereas binding energy we got 536.42 mega electron volt. So we need energy in joules. Therefore what you can see, 153.84 into 10 raised to 23 mega electron volt. We know electron is 1.6 into 10 raised to minus 19, right, and M is 10 raised to minus 3. So apply it, you will get 2.55 into 10 raised to 12 joule. Students, once again I'll repeat, you have to convert mega electron volt to joule. So mega electron is nothing but 10 power minus 3 or 6 plus 3, 10 raised to 6, 1.6 into 10 raised to minus 19. If you into this, you'll get this answer. Obtain the amount of cobalt necessary to provide a radioactive source of 8 millicurie strength. Half-life of cobalt is 5.3 years. What is given? Half-life of cobalt is given, that is T half is given, it is 5.3 years. Then activity is given, A, that is 8 millicurie. Now we have to find N. Let us convert this to seconds. How we can convert? 5.3 into 365 into 24. Year, hours, 24 hours, 60 minutes, 60 seconds. Therefore we will get some 1.67 into 10 raised to 8 seconds here. If you convert this, 8 into millicurie is nothing but 3.7 into 10 raised to 10, and milli is 10 raised to minus 3. 1 curie is 3.7 into 10 raised to 10, and milli is 10 raised to minus 3. Therefore we will get 29.6 into 10 raised to 7 decay per second. Okay, disintegration per second. Okay, then what we need? Lambda, which is given as 0.693 divided by T half, right? T half we have. So directly let us substitute. We know activity A is given as lambda n. N is nothing but A by lambda. Substituting, A is 29.6 into 10 raised to 7 into T half, that is 1.67 into 10 raised to 8 divided by 0.693. After calculating, we will get some value, that is 7.13 into 10 raised to 16 atoms. In this way you can calculate this. So this is N. So what was the question then? Obtain the amount of cobalt necessary to provide a radioactive source of 8 millicurie strength. Half-life of cobalt is were given, right? Now we have found out N. Now we have to find the mass of 7.13 into 10 raised to 16 atoms. That is, we have to find M dash. Now we know the formula, that is N is equal to Na M dash by A, right? So we know Na, A and N, we don't know M dash. So we have to find M dash. M dash is nothing but A into N by Na. A is nothing but the mass number, that is 60, and N is, we have found out this one, Na is 6.023 into 10 raised to 23. So we'll get the answer 7.106 into 10 raised to minus 6 gram. So this much of amount of cobalt is necessary for the purpose. Now next question is, calculate the half-life and mean life of radium-226 of activity 1 curie, given the mass of radium is 1 gram and it consists of 6.023 into 10 raised to 23 atoms.